So let's begin. All right. The formal definition that we're going to be using and working with is this. A matrix. A matrix is just a rectangular array, yep, of numbers. Array is like a string of digits, A rectangular array of numbers used to solve systems. So this is a pretty traditional definition of a matrix. It's a rectangular arrangement, or they call that an array, of numbers used to solve systems of equations. So let me give you an example of what we're going to be dealing with. So most of the time we define a matrix as a capital letter. So I'm going to define matrix A, and it would look something like this. 2, 4, 1, 6, 5, and 3. This is an example of a matrix. It's a rectangular array of numbers that can be used for various things. One thing that we do use is we use them to solve systems. So this lesson is all about just getting accustomed to them and, of course, adding, subtracting, and multiplying them, because that's what it says up at the title. All right. Every single matrix has what is known as an order or a dimension. And in this case, I use the word order because that's how I learned it in my grad school and school that I was growing up with. The book uses the dimension. Okay, so the word order and dimension mean the same thing. And this particular matrix has an order of 2 by 3. What do you think I mean by a 2 by 3? Yeah, Nick, what do you think, buddy? Yeah, 2, no, not 2. Oh, okay, too tall. I see what you're saying. The 2 right here stands for the rows. That's a row and that's a row. So call those rows, okay? Yeah. So you're on the right track. So 2 is going to be rows. And the 3, exactly, which I'll do in a different color for you, like green here. The 3 is going to stand for the columns. So column, and that column there. So the 3 stands for the columns. Okay? So think of it like, thanks, James. So rows, kind of like, think of like the dresser drawer of like at your home, like a dresser drawer, usually like top drawer, middle drawer, bottom drawer. Those are your rows. Columns, I always think of like the Roman Colosseum. They're like up and down. So that always helped me when I do it, right? Yeah, thank you. I made that up myself. So a 2 by 3 matrix is referring to the order of the matrix, also known as the dimension of the matrix. Now, what else is interesting or to note is how we actually talk about these. So for example, this right here that I just circled, that's the number 4, obviously. But more importantly, it is an entry. An entry or an element. I think the book uses both. So matrices are made up of elements that are in an array of numbers. So we call this element A2, 1, 2. Almost lost all the time now. A1, 2. What do you think the 1, 2 subscript stands for? Yeah, exactly. A1, 2 stands for row 1, column 2.
Oh, so that's not 12.
That's not a 12. No, it's A1, 2, not a 12.
What if it was, what, like, how do you distinguish that? Should there be like...
Yeah, that's a great one. What would this one be? Row what? Row 2, column 3. Very good. How about this one over here? What would this one be? Yeah, that'd be a row 2, column 1. Very good. What about this one here? Yeah, row 1, column 1. How about this one over here? Row 1, column 3, A1, 3. How about this one here, since we're doing this? Yep, that says 2. 2. Okay, so therefore we can now actually be really specific about the elements of the matrix or the entries of the matrix, all right? All right, in order to add 2 matrices, you have to be sure of one thing before you even begin. The 2 matrices must have, if you had to take a guess, what do you think they must have?
Rows and columns.
Yeah, they must have the same order or the same dimension, right? So the same order or the same dimension, okay? In order to add them, in order to add two matrices, you must have the same order or the same dimension. So let me give you an example, right? I would define matrix A as being 1, 2, 3, 4, 5, and then 8, just to, make things interesting. And then matrix B would be, how about 0, 1, 5, 2, 6, and then 3. All right? So, what is the order of matrix A, or the dimensions of matrix A? Rows by column.
3.
This is a 3 by 2. What's the order or the dimensions of matrix B? Also a 3 by 2. Do they have the same order? They have the same order or dimension, so therefore I am allowed to add them. Okay, so if I was interested in adding these two matrices, A plus B, it would result in another 3 by 2 matrix. Now, if you just had to take a guess for $1 million and you only had one guess, what do you think it might be? Decky, what would you say?
You add 1 and 0, 3 and 5, 5.
Okay, we are very sophisticated now. What do we call these? These are corresponding elements. There you go. Corresponding entries or elements, right? So that'd be 1 plus 0 on a good day is how much? That's still 1, right? Okay. So 2 and 1, this would give me 3. 3 and 5 is 8. 4 and 2 is 6. 5 and 6 is 11. And then 8, 9, 10, and 11 again. You guys agree with that statement? All right. So adding matrices, pretty straightforward. What must you always consider when adding a matrix? They must have the same order or dimension. So, ladies and gentlemen, if we know how to add two matrices, what do you think we do for subtracting two matrices? We do the exact same thing. It's exactly what you'd expect to do. All right, so I've got two matrices, A and B, defined here for you. And I am interested in subtracting these two matrices, or subtracting B from A. So what is the order of matrix A? Rows by column, row by column. This got 2 rows and it has 3 columns. Matrix B also has 2 rows and 3 columns. Therefore, if I'm interested in subtracting, if I want A minus B, I would also create another 2 by 3. Okay, the most common mistake made by students in this particular problem is not distributing the minus sign through. So I want to call attention to that now. Make sure that you're aware of it. Make sure you don't do that mistake, okay? So this will be 3 minus 1. That's just 2. No big deal. 2 minus 4, negative 2. 4 minus 3, 1. Negative 1 minus negative 2. 1. Value of 1. Very good. 4 minus 2, 2. 0 minus 4, negative 4. So this is what our answer should be. Okay, at this moment in time, I want to show you how to do this in your calculator. So please take your calculators out and follow along with me. So here's that. Clear this up. All right, here we go. I'm going to show you how to do this. Where can I put this? Hold on. I'm going to shrink this down a little bit so we can see it. Okay, hold on a second. Here we go. All right, so I'm going to show you how to plug this into your calculator. So if you hit second and then this x to the negative 1, you'll notice that the matrix folder comes up. Okay? Now, right, see this red button, Rachel? That's where you're going, okay? Okay, please follow along. You have a choice. We want to notice that your calculator can store about 9 or so, maybe even more matrices. All right, that's nice. Right now, my calculator has stored in matrix A a 2 by 2. Yours may not have anything in it, and that's okay. No big deal. So I'm going to show you how to enter in matrices into your calculator. We need to go to the Edit button. One quick way to get to the Edit button is just push your arrow to the left. One button, it'll go all the way over. Save you one keystroke, okay? So now I'm in the Edit button, and I'm going to edit matrix A. So I'm going to push Enter. Please push Enter as well. Okay. So now, when you push Enter, you have to tell the calculator the order of the matrix you wish to enter. I want to enter in a 2 by 3. So 2, and then Enter, and that moves your cursor over, and then a 3, and then Enter. And notice the calculator gives you a 2 by 3 setup to enter in your individual entries. Because I did this last block, I just used a different one, okay? So now, how do I want to enter matrix A into my calculator. So I'm going to go 3, enter. And notice as soon as you push enter, the screen field automatically jumps to the next column. Stays in row 1, but it goes columns left to right. So I'll punch in 2, enter, and then 4, enter. And now I'm in row 2, column 1. So I want -1. Hey, you guys, be sure you use the negative sign, which is the button below the 3, not the minus sign. There's a difference there. Enter, then push 4, enter, then 0, enter. And we have now successfully stored in matrix A into our calculator. So when I hit second quit, the actual matrix is still in my calculator. It hasn't gone anywhere. And you can check by going back to the matrix folder menu, and you'll see now I have a 2x3 in there, and it's exactly the one that I entered. All right, let's enter B as well. So let's go over to the edit button, go down to option 2, and enter in your 2x3. So 2, enter, 3, enter. I want to enter all of these. So I'm going to go 1, enter, 4, enter, 3, enter, -2, enter, and then 4, enter. Oh, I did something wrong. Oh, I forgot my 2. Thanks. 2, enter, and then 4, enter. Okay, make sure you take your time and do it right. Otherwise, you're going to mess up your math. All right. Once we've got that in there, we can now do operations on the 2 matrices that we have. So for example, if I hit second quit, I get back to my main home screen here. If I'm interested in A minus B, I can just go second matrix, and I can call that 1 because that's what matrix A is defined as. Second matrix 1. And then I want to subtract second matrix 2. So there, in my screen, here's A minus B. That's what it says. When you push enter, it should give us exactly what we figured out. 2, -2, 1, 1, 2, and -4. All right, this particular section also introduces the idea of a matrix equation. And it's exactly solved the way you would normally think it would be solved. So as an example, if I gave you this, if I gave you some number plus A equaled some different number, what would you do to solve this little simple equation? You would just subtract the matrix. You would subtract 3 from the 7, right? Well, you do the exact same thing with matrix operations. So this A, assuming that this matrix is indeed still a 3x3, under that assumption that there's a solution to this particular equation, it would just be this big matrix: 8, 11, 9, -5, 5, and 2, 10, 7, and 8, subtracted from what we had before: 1, 0, and 12, 3, 5, and 9, 7, 8, and -2. So I'll save you a little bit of work here. I already worked it out. Obviously, this would just be what it would be. Since the 2 matrices are both 3x3s, they can be subtracted from each other. So you would fill this in and you would go. Okay. The 0 matrix, just like the number 0 in real numbers, also does exist. So for example, if I called this matrix A and I called this matrix B, we would say that matrix B is the additive inverse of matrix A. B is the additive inverse. The reason it is because that when these 2 matrices are added together, we get what's known as the 0 matrix. So the whole point that the book wants to point this out to you is that so far, adding 2 matrices and subtracting matrices and the additive inverse of matrices is exactly the same structure as it is for real numbers, right? We can add real numbers, we can have the additive inverse for real numbers, and we can subtract real numbers. So far the structure is still the same. You might even think that the structure is unanimous, meaning that whatever you can do with real numbers, you could also do with matrices, and you would almost be right. There is a few special differences which we're going to talk about today. So the additive inverse does exist, and that would be what we call matrix B here, and the result would be the 0 matrix. So when you hear the terminology 0 matrix, this is what they're referring to. For the same token, 2 matrices are equal. 2 matrices are equal. Okay, if you had to take a guess, if you had to take a guess, what would make two matrices exactly equal? What do you think it would have to be? If what? There's two conditions that have to be met. If they have the same dimension, right, or the same order, right? So whatever, m by n, that has to be the same. And what else has to be the same? Yeah, what do we call these things? We call them, yeah, corresponding elements. Okay? So you are allowed to say two matrices are equal if these two conditions are met. One, they have the same order, and two, all corresponding elements are exactly the same. For example, let me give you a quick, here's 0.25, here's 1.5, -3 and 4/5. And here's another different matrix, which is a fourth, 1.5, -3, and 0.8. These two matrices are equal because they meet the two conditions. This is a 2 by 2, this is a 2 by 2, so their order is the same, and every corresponding element is the same value. It's pretty straightforward. It's exactly what you think it would be. That and that are the same, and then 1.5, and then 1 and 1 half are the same. Okay, here's an example where we can actually take advantage of that equal sign. If we truly take a moment to understand, okay, well, if indeed these two matrices are equal, then two conditions have to be met. They have to be the same order, which they are, they're both 2 by 2s, and every element needs to be the same value. So that means that 3x plus 1 has to be a value of 16. So 3x plus 1 is a value of 16. So 3x must be 15, so x must be 5. That is a totally acceptable way to solve for variables with the matrices, given that the two matrices are equal. So here's another one, right? 2y minus 1 must be equal to -5 because they're corresponding entries. So we say 2y minus 1 is -5. So 2y must be -4. Y must be -2. There you go. Just make sure everyone's around. Okay? Okay. Scalar multiplication. So we begin 12.2 by talking about scalar multiplication of matrices. Now, have you guys taken any kind of physics whatsoever so far?
Yes.
Yeah, okay. Well, remember when you talk about vectors, there are scalars, right?
Oh yeah.
And vectors,
One
right?
has size and direction, the other just has size.
Yeah, exactly. What? So magnitude and direction, or just magnitude, right? So in this case, a scalar would be something like this. If I wanted to take, 2 times the matrix, 5, 3, -1, and 4, the matrix 2 is acting like a scalar here. It scales the matrix up or down. So what do you think this is going to do to the matrix? Would this make it a 4 by 4 ordered matrix? Do you see why some people might think so, though? Right? I'm doubling my order. Some people might think so. That's fair enough. But indeed, what's really going on is this just doubles every entry, right? So that gives me 10, this gives me 6, this gives me -2, and this gives me 8. That's really all scalar multiplication does. Now, is my scalar allowed to be a negative number? Sure, why not? It's allowed to be a negative number, right? Is my scalar allowed to be 0?
Yes.
Sure, right? Just like it is in regular real numbers, right? Any number times 0 is 0. Any number times 1 is itself. Any positive times a positive increases. Negative times negative increases. All that's still true, right? Okay, so I've got two matrices defined for you. And I am interested in the result from 2a plus 3b. Well, it's exactly like you think it would be. It'll act exactly as you would expect it to act. So far, everything is pretty harmonious with the real number system. Okay, so that says 2a plus 3b. All right, so what do you think we do? Well, 2 is acting as a scalar for a, and 3 is acting like a scalar for b. So 2 times a would give me matrix what? 4, 16, -6, -2, 10, and 4. Very good, awesome. Okay, if I want to add 3b, it would give me what? What's 3b? -3, 0, 15, 0, 9, -6. Okay, we have a very fast multiplying going on.
Isn't that supposed to be
Okay, negative 16. No, 2 times 8, that's 16. Yeah, I think that's good.
Oh shit,
Okay.
I'm looking at the wrong.
Wrong way. All right, now if I want to add these together, they have the same order, so I'm all good to go. What would my resultant be here?
116, 9, negative 2, 19.
116, 9, negative 2, 19, and negative 2. Okay, great. So if you had to do that in your calculator, what do you think you would do?
You have to press the 2.
You would go 2 times A. You would enter A, enter B, and go 2 times A plus 3 times B, and you should get the same exact result. Okay, we actually get to something a little bit more interesting and somewhat deviates from the real number system. All right, as a side note over here, everyone in the room agrees that 7 times 3 is the same thing as 3 times 7. True or false? It's exactly the same thing, right? The result is the same thing, right? The reason is because what property is this called? Commutative property. There you go, right? It's commutative property, right? So 7 times 3 is the same thing as 3 times 7. This is true. However, ladies and gentlemen, A times B is not the same as B times A. You don't get commutativity with matrix multiplication. It just does not work out the same way. So this is where the structure of matrices differs from the structure of the real number system. All right? You don't get commutativity. So here's what we're going to do. I have matrix A, I have matrix B defined for us. All right? We're actually going to use our calculator right now to plug in A times B and B times A and look at the result for each one of those. So let's go ahead and do that together. So bring your calculator up. All right, go to your matrix, second matrix, and we're going to edit matrix A, and we're going to make it a 2 by 2. 2 by 2 enter. So I'm going to put 2, and then 1, and then negative 3, and then 0, enter. All right? So far, so good. Okay, and then go back to second matrix, and go to edit, and go to matrix B, and let's enter in matrix B, and matrix B is this one right here. So we'll say it's a 2 by 2, push enter, and it's negative 1, enter, 3, enter, 0, enter, and then 4, enter. Yeah. Okay. Alright, so we'll hit second quit. I'm going to clear my screen just so I can have a nice clean picture of everything. So I am interested in A times B. So second matrix 1 multiplied by second matrix 2. So that says A times B, and I get this. Negative 2, 10, 3, and negative 9. I'm going to write that down real quick so I don't forget it, okay? Over here in purple. So it was, what was it? A times B? Negative 2, help me out. 10, 3, negative 9. Good. Okay, did you guys do B times A? What'd you get for B times A? Negative 11, negative 1, negative 12, and 0. Okay, woo! Yep, clearly this is the case. A times B is not the same thing as B times A. Huh. What's going on? Okay, let's dive into this a little bit deeper. So I don't need this anymore, and I don't need this anymore. All right, it doesn't make any sense, right? Okay. Well, here's the first thing that we have to understand when multiplying two matrices. The order of the matrices matters. And the order in which we're doing them matters. So the first thing we always do is we write down the order of matrix A, which is a 2 by 2. We also write down the order of matrix B, which is a 2 by 2. Okay? So here's what has to be the same, okay? Exactly. Here's what has to be the same. In order to multiply two matrices, I'm multiplying A and then B. So A's on the left, B's on the right. So I take the columns, right? It's row by column. So column of matrix A has to be matched up to the row of matrix B. These two inner numbers must match. They must match. Ladies and gentlemen, if they do not match, then they cannot be multiplied together. So for an example, a 3 by 5, right, matrix can be multiplied by a 5 by 2. Why can they be multiplied? That's right. So I can multiply it because the 5s and the 5s match up. Now here's the cool part. Okay? Whatever is on the outside, so I'll do this in a different color for you so you can see. The 2 and the 2, the leftover part, this will be your result. So what do I mean by that? Look, it's another 2 by 2 matrix as the result. See that? Oh. So look over here, my other little example. A 3 by 5 and a 5 by 2 will result in a what? Will be a 3 by 2 resulting matrix. Okay? I'm going to show you how in a second, but this is the first part that we have to understand. Rachel, you had a question. I am very curious as to what the calculator is doing to get that answer. So I'm going to show you how to do it. Nope, it's the same box here, okay? So here's the deal. I'm going to show you how they got the answer of negative 2, 10, 3, and negative 9. So we're going to do A times B. The resulting matrix is going to be a 2 by 2, and here's what I want you to do. I want you to draw a giant 2 by 2 matrix. Turn the page over. Okay. A giant 2 by 2. All right? And then next to it, we're going to draw a little 2 by 2, because this one over here, this one in the blue cloud, this is going to be our answer. Okay? And our answer should be negative 2, 10, 3, and negative 9. That's the very answer. Now, we know this ahead of time, but normally when you do this on your own, you wouldn't know this ahead of time. But so you draw a big one, and then you draw a little one next to it. Okay, what do you do with the big one? Here's what you do with the big one. You have a question. All right, here's the next part of the setup, all right? You need to draw yourself 4 spaces inside the big 2 by 2, okay? Because your answer is a 2 by 2, so you're going to have a big 2 by 2. And inside the big matrix here, you're going to label where each of these are. So as an example, what I mean by that is this position is row 1, column 1. Agreed? This position would be row 1, column 2. So far, so good. Everybody still with me? Hello? Yeah? Yeah. This position would be row 2, column 1. And this is row 2, column 2. All right? Now, here is what you need to do. We're going to multiply row 1 of matrix A with column 1 of matrix B. We're going to multiply that together. How do we do that? Well, we multiply corresponding entries and we add their result. Here's what it will look like, right? I'm going to take 2 times negative 1 and write that down here. 2 times negative 1. Notice that I'm not doing any calculation in the big, huge matrix. I'm going to add to that 1 times 0. 1 times 0. So there you go. There are the entries of row 1 multiplied with the entries of column 1 from matrix A and matrix B. Notice that this is a value of negative 2 plus 0, and that is where the negative 2 comes from. Crazy, right? Okay. All right, let's move on. Let's do row 1 with column 2. So row 1 with column number 2. All right, here we go. That means I'm going to have 2 times 3. Notice that I do not make any calculations because there is so many times where we can make simple little errors. It's not worth messing it up on this stage of the game. I'm going to add to that 1 times 4. 1 times 4. Then I'm going to figure that out. 2 and 3, that's 6 plus 4. Hey, that's where the number 10 comes from. Ah, okay. Let's do row 2, column 1. So I'm going to go row 2, and I'm going to go column 1. All right. Well, that's going to be this. Negative 3 times negative 1 plus 0 times 0, that's just going to be 0. Right? And then negative 3 times negative 1, that's where the positive 3 comes from. Similarly, to finish up the problem, row 2 by column 2 would look something like this. Negative 3 times 3, that would be this one times this one, plus, well, I see a 0 in there. That's really nice. That's going to knock everything out for me, right? And look, that value is where the negative 9 comes from. Okay, here we go. I'm asking you to multiply A times B. A 2 by 3 by a 3 by 1. Can you even do it? Yes. What will the result be? 2 by 1. 2 rows, 1 column. Ready, set, go. Check it in your calculator when you're done. Okay, when it's all said and done, you should get 0 and 42. Now, what would happen if in the calculator you multiplied B times A? What would show up? No, not the same thing. You would get a dimensional mismatch, right? The calculator is going to say a dimensional mismatch because if I switch these around, I would be taking a 3 by 1 times a 2 by 3, and those numbers do not match up.